Hi, Math 170. We have finally made it to chapter 4. I don't know about you, but chapter 3 took forever to get through. So these sections are going to be a little longer because I do show more examples, but I guess the good news is there's less sections in chapter 3 than there are in chapter 4. And before I start chapter 4, I want to kind of go over a little bit of preliminary work that might help you with some of the ideas to help with analytical geometry that's involved with these problems. So, having said that, let's look at some summation formulas that we want you to look into memorizing. See if I can help you out with this. You see these really more common in the integrals that we'll be dealing with. And also we end up studying series a lot more in Calculus 2. So, I mean, it looks like they enter our lives briefly for this first section in 4.1, but you will utilize them a lot in Calculus 2. So having said that, we're looking at the sum of all the numbers. The counter goes from I equals 1 to any number, n. Remember, these are all integers as we're counting. And so from our pre-calculus, or even if you don't remember, I will help you out with that. There's a formula, so you don't have to actually add all the numbers up. That is actually taking whatever n is, multiplying it by n plus 1, and dividing that by 2. So instead of, if you see those summations show up, you can now replace that with that expression. There's also the sum of all the squares of integers from 1 until n. And that formula is best described as n times n plus 1 times 2n plus 1 all over 6. And then you'll often see the sum of cubes as well. So it's very much related. I don't know why it looks a little nicer to me, but it's related to item number 1, n times n plus 1 over 2, except we're going to square it. And if you're interested, you can kind of go back and see the proofs for these. They're quite clever. You kind of, I know item number 1, you probably heard the story about Gauss doing this when he was in school to avoid having to actually add up all the numbers from 1 to 100. So feel free to look into those stories. They're entertaining. But let's just kind of work on utilizing these formulas. If we're actually given what the counter is and what n is, we could actually plug them in and find the actual number. So we'll just start off nice. If we're looking at the sum of all numbers 1 through 5, by the way, if you're still getting used to this summation notation, what is this standing for is you're looking at where to start. That's I equals 1. So that's going to be 1. And then you count up with integers, 1 plus 2 plus 3 plus 4 plus 5. And that's great when it's just 5 numbers. We could actually find the sum, but the actual formula ends up being a little faster when we get a little higher. Like if you want to add all the numbers up from 1 to 1,000, we're not going to sit there and write out the sum. But it is important to understand what summation notation really is talking about. So if we could kind of compare, the top number is n. So we should have 5 times n plus 1, 5 plus 1, all over 2. And then sometimes if you are interested, you can reduce. So sometimes you'll see me say 5 times 6 over 2, and then I take a little bit of liberty in saying, well, 6 over 2 is 3, 5 times 3 is 15, and we actually have the actual sum. And if you want to check to see if I'm not lying to you, go ahead, add up all the numbers, 1 plus 2 plus 3 plus 4 plus 5, and we should get 15. So similarly, we could do the same thing, just so that you understand what we're talking about with summation notation. The counter starts at 1, I equals 1. So we'd be looking at 1 square. Then we plug in integers, plus 2 square, plus 3 squared plus 4 squared, and then we stop at n equals 5. So that'd be plus 5 squared. And also, this is not horrible to plug into our calculators and find the answer to, but if we don't know where to stop or we have really high numbers, we would really want to utilize this formula. If you want to look back just in case, that would be n, so n is 5, 5 times 5 plus 1 times 2 times 5 plus 1 all over 6. And so if we want to simplify just a little bit, what do we get? 5 times 6. 2 times 5 is 10 plus 1 is 11 all over 6. And it's kind of nice. You see how the 6's divide out. So 5 times 11 gives us 55. And again, feel free to check. That's not a horrible, these aren't really horrible to add up. I just want to show you how they're being utilized. And then part C, just so that we can fully see all 3 formulas being put into play. We're going to look at I cubed. So what is that telling you? Starting at 1, you're plugging in 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. To utilize the formula, that is n times n plus 1 over 2, and we're going to square this. So what does that look like? N is 5. 5 times 5 plus 1 over 2. And don't forget, we're squaring this because this is a cubed formula. And I say square, that's what I meant. So we can simplify this. So what do we have? 5 times 6 over 2. We kind of figured this out a little earlier. If we're squaring this, we should get 15, but it's 15 squared. And 15 squared, 15 times 15, either use your calculator or if you know, it is 225. So that's kind of utilizing the formulas. In our case, maybe a little bit more down the line in the section, we might be utilizing these in terms of just n. So make sure you kind of have these formulas in your mind so that you can pull them out when needed when you're trying to justify some of these problems. So that's the first idea. Second idea before we start 4.1 is the idea of dividing an interval into subintervals. And you'll kind of notice it's not too complicated, but I want to kind of go over some of the preliminary notation. That's kind of what makes it feel like it's more complicated. But you guys have all divided intervals into subintervals. You kind of know how fractions work. But I like to show you how it works with the notation that we will be utilizing in this section. So example 2 is asking us to divide the interval from 0 to 8 into 4 equal subintervals. And a lot of times what helps me with this is I like to kind of draw the picture off to the side. It's kind of a number line that you're breaking up. And it really does help to understand the endpoints of the interval. And that is our 0 and our 8. And I know you've done this before. This is not horrible if you have just numbers that you're dealing with. So we can do that just so that for purposes of understanding the idea of the problem. If you break this up into 2 equal subintervals, that's us breaking the distance between 0 and 8 and 1/2. And so that number would be a 4. But we want 4 equal subintervals. So what we're going to have to do is apply maybe half of a half. So if we cut this distance from 0 to 4 into half, or 2 pieces, then that should be a 2. And then again, the distance between 4 and 8 into 2 equal parts, that would be a 6. And so you've done this before. That's not a big deal, but I kind of want to look into what we're really dealing with here. There's 2 things to play with notation-wise. We're going to look at subinterval width. And we are going to talk about what that means is the distance between any 2 numbers in the subinterval. And so we're going to define this as delta x. That's what the triangle, change in x. And the way we find it, you kind of probably realize that it's a formula where you take the endpoints of the interval. So in each case, you're saying the larger value, 8. You subtract off the first number in the interval, and you divide by however many intervals that you want. So we wanted 4 of them, so we divided them by 4 to get the 4 equal subintervals. So then we can see when we do the math, the length of delta x should be 2. And I know we were able to intuitively do that for each of these subintervals, and you can see it put into play, but I just want to give you the notation. Because maybe we won't know the actual length. So that's going to be something to look at later. The other thing I want to point out is I'm going to be looking at endpoints of each of the subintervals. And we start using, you probably guessed it, if we're using summation notation earlier, we might be using subscripts to denote some of these. So if I could start labeling what my numbers are, usually we start off with the x sub 0. That's always the leftmost endpoint, so the beginning part. And so in our case, the number-wise, it was equal to 0, and just kind of keep in mind it's the leftmost endpoint. And you'll probably guess, well, what are we doing? We're going to be counting upwards just so that we can see. So we have x1, x2, x3, and x sub 4. So that's not too bad. You could kind of notate that. But how does this work in terms of our subinterval width, notation-wise? I know we can see the numbers. I just want to show you formula-wise. I should have x1. Now what this does is it takes the previous endpoint and it adds on the distance between each of the subintervals. So that would be adding on, in our case, delta x. And if we were to do that, remember the delta x, I can even give you that, just so that we notate this. It's the distance between any given subinterval. Who was our x0? That's 0. If we want to figure out what's the distance between 0, and then we add on whatever delta x is, which is a 2. I should probably give you that so you can see that. Then we end up having what our second endpoint is, x sub 1. And you could kind of say, oh yeah, we already marked it. Just so that you see the pattern, if you want to look at x sub 2, and you want to relate it back to the leftmost endpoint, again, you can start off with x sub 0, but kind of keep in mind how many delta x's will you be adding on. There's 2 subintervals, so that's where we're getting the 2 times delta x. And so then you could kind of see, oh yeah, that's the same thing as 0 plus 2 times 2. And that's where we're getting the 4 for our denotation of the endpoint. And you'll probably, you being in math, you like patterns. What do you think x sub 3 is? So we're trying to see how many delta x's do we add on to our leftmost endpoint. There's 3 delta x's. So our leftmost endpoint 0, we should have 3 times 2, and that's where we're getting our 6. And you're like, yeah, I see it right away. And finally, your rightmost endpoint. And even if you don't know where you're stopping, you'll know because you're reaching the end of your interval. We're starting out at the leftmost point, figuring out how many delta x's are we adding. They should be 4 of them. And so we start off with 0 plus 4 times 2. And yeah, we're verifying we just ended off with 8. And by the way, that is the rightmost endpoint. And so all of this kind of seems obvious if you're actually drawing out the number line. So I really recommend that you do that. If it's nice for you to do so, draw a quick little sketch so that you can really determine who's your x of 0, who's your x 1, 2, 3, and 4. And then you don't necessarily have to use the formulas, but it's helpful to understand the relationship should we need to use these later for more complicated values. So let's do this with example 3. Makes it a little more exciting. We want to divide the interval from 2 to 4 this time into 6 equal subintervals. So I'll sketch it out and then we can decide what everything looks like. Again, if we were looking at the intervals, we're going to talk about our endpoints. There's a 2 and then there's a 4. Now, if you're going to divide it into 6 equal subintervals, you could kind of play around with the idea of fractions. If you cut it in half, that's 2 equal subintervals. I'll do my best to see exactly where the half point is. Now, if you cut it in half again, you only have 4 equal subintervals. So to make 1/6, you'd have to cut each half into thirds. So do the best you can. We have to eye it here. And then if you're not sure, you can just double check if you're counting each length. What do we have? 1, 2, 3, 4, 5, 6. So we are good to go. So now we have a picture of what we're dealing with. And yeah, we can do the math without needing any sort of formula. But what I'd like to kind of point out for you is if you can name each of these pieces, we're going to be in good shape. So remember, we always have x of 0 is the far left endpoint. And then just count. We can label this x of 1, x of 2, x of 3, x of 4, x of 5, and then the rightmost endpoint is x of 6. So now we have names for all of these, and we just want to find the values. And so we go back and we say, okay, we want to know what this subinterval width is. And these are nice numbers. We don't have to play too hard with it, but we should have delta x. And so that's what I'm looking at right here, the distance for one of the intervals. And it's always the left endpoint and right endpoint. So let's do the right first, the bigger number, 4. Right endpoint minus left endpoint, all over however many subintervals that you want. So we wanted 6. So what do we have? 4 minus 2 over 6. That's going to be 2/6. And that's great if you want to use it, but I like to reduce, make my life a little easier. So I should have 1/3. So that's, now we know the distance between each of the intervals. And now just by counting, you can say, oh yeah, well, x1 is 2 plus 1/3. x2 is 2 plus 2/3. And that's fine. Let me just help you out though with notation, just in case we have to use it. So take your time on this. And we kind of keep in mind our x of 0 was already defined as 2. X sub 1 is equal to x of 0 plus just a delta x. In our case, it's 2 plus 1/3. And that would be 2 1/3. If you'd like, you can change it to improper fractions if that's something that you're interested in. Right now, I don't bother. And yeah, that does make sense. 2 plus 1/3, yeah, that's where we're going to get x1. x2. So you start off with your left endpoint and you add 2 delta x's on. Keeping in mind, just remembering that your delta x is equal to 1/3. So remember, this is not 0 that we started with. We started at 2, but we're adding on 2 delta x's, so 2 times 1/3. So what is that? 2 plus 2/3. Well, that's 2 2/3. I'll keep the mixed number format. It's easier on my eyes. Let's keep going. x3, x of 3. So we start off with the left endpoint. We add 3 delta x's on. That's 2 plus 3 times 1/3. 3 times 1/3 is 1, so we should get a 3. And if you're interested, you could attach numbers if that's something that you're interested to see. And you could have probably done this before we set up all these formulas. I just want you to see the connection. Keep going. X of 4. Leftmost endpoint plus 4 delta x's. So that's 2 plus 4 times 1/3. And so what is that? 2 plus 4/3. And what is 4/3? 1 1/3. So that should be 3 1/3. And technically, if you knew what x3 was and you're just adding on 1/3, yeah, that totally makes sense. No problems there. So x of 5 Leftmost endpoint, add on 5 delta x's. That's 2 plus 5 times 1/3. So that's 2 plus 5/3. And 5/3 is, what is that? 1 2/3? So that should be 3 2/3. And yeah, that makes sense. 3 1/3 plus another 1/3 is 3 2/3. So we're just verifying that it should be making sense. And verify one more time our x sub 6. Start off with your leftmost endpoint, add 6 delta x's on. That's 2 plus 6 times 1/3 gives us 2 plus 6/3. And 2 plus 6/3, 6/3 is actually 2. So that should give us 4. And yes, we have just verified that those are the names of the endpoints. And by the way, that is your rightmost endpoint. So far feeling okay? I always like kind of demonstrating with concrete numbers first, and then we're going to look at maybe we can deal with some of the abstract. So just a little bit more, just to kind of add on to what we just did. Sometimes they don't tell you the size of the subinterval. They just want you to say n equals subintervals. So we're going to use the same idea. For some reason, some of this got deleted off, so I will do my best to help out. So let me see if I can pull up 4.1 with you. So just so that we see this a little bit more clearer, if you're trying to get n equal subintervals, what we did earlier, it was always the leftmost endpoint and the rightmost endpoint would be involved in your subinterval width. And a lot of times, instead of calling them, 0 and 8 with nice numbers, you end up saying that the first leftmost part is called B, the rightmost endpoint is, excuse me, I'm getting my lefts and rights confused already. The left endpoint is called A, the right endpoint is called B, and that's where we're getting our particular formula from. The number of subintervals is called n. And so you notice if we wanted subinterval width, b minus a, 8 minus 0 over 4 subintervals. So I'll kind of demonstrate this just in case, but if you want to draw a line really quick, do I have shapes I can do? I'll just go freehand, the best that I can. And if you know that your leftmost endpoint's A, your rightmost endpoint's B, well, you have your delta x. And what we want to look at is if you're dividing it into n equal subintervals, that means we really don't know what the size is. What happens is we just keep going until we can no longer stop. So we kind of know, okay, so far they have to be equal size, and the size of any equal subinterval is delta x. And if you're going to start naming them, remember, the leftmost, it could be called A, but it's x sub 0. Then the next endpoint is what? X sub 1, then x sub 2, then x sub 3, and then we don't really know what's happening. So what ends up happening is they kind of cut out a distance because we're not sure. So let's say we start up again. We're not sure what this means, but I do know I have to make it the length of delta x. So maybe from here to here, still delta x. And so any given point in the subinterval, the name of the point, they call it x sub I. And you're like, oh, that's where the i's are coming from with that summation notation. So if we're looking at this generic subinterval, we call this the ith subinterval. And then what happens is if you're trying to label it, what do we have? X sub I minus 1, because they're always 1 apart. And then you could keep going. We don't know what we're cutting this up into, but at the end, what do we have? I'll try to make this a little bit clearer. Again, that's delta x here. We would have b is x sub n. And if we're trying to name the endpoint that's at the beginning of that nth subinterval, then we know that they're 1 apart from each other. So that name of this one would be x of n minus 1. So you kind of play around. And I'll kind of, when I pull up 4.1, you'll kind of see that we repeat ourselves indefinitely on this sort of idea. So the idea is to break from concrete to a little more abstract, and then just kind of know what we're dealing with. So hope that helps out. Let's move on to 4.1, the actual formal notes. We'll do this in the same video while we're here. And here we go. So let me widen this out for you all. And same story. For breaking this up into subintervals, want a little more practice? Let's do it. So let's draw this one more time. I'll take my A and my B. And then if we're kind of breaking things up into subintervals and we want to have a certain distance apart, they're all going to have the same distance. So the delta x part is the b minus a over n. So this first one that I highlighted, what do we call this? The first subinterval? And the, let's write that a little nicer. So first subinterval. I don't know if that's nicer, but try to write bigger. We'll see. So if you're looking at the first subinterval, the endpoints would be a, which is x sub 0, and x sub 1. And then kind of you're playing around. If you're counting, we have x sub 2, x sub 3, and then if we have a break because we don't know how far we're going, we can start up again with the same distance, just in case we're wondering. And this is what they called the ith subinterval. And so if you're kind of playing around with those endpoints, if it's the ith subinterval, we have the x of I, which is the right endpoint of the ith subinterval. And then the x of I minus 1 is the left endpoint of the ith subinterval. Not to be confused with the endpoints of the interval you were trying to break up. So remember, A is the leftmost point in your actual interval, also known as x of 0, and B is the rightmost point, also known as x of n. And so if you're actually finding this out, and this is what we were developing in the preliminary work, the name of the endpoint is calculated by however many distances delta x is away from the original endpoint. So we can play with the formulas if you're interested. You can kind of see how this works. If I have x of 0, I have a plus, well, if I is 0, we don't have any delta x's. X of 1, it's a plus 1 times delta x. X of 2, a plus 2 delta x's. And then you can kind of play around. X of I minus 1s, what is that? A plus I minus 1 delta x's. X of I, a plus I delta x's. And you want to play a little further, the x of n, I'll bring it down further. that's a plus n delta x's. And by the way, that's equal to b. So we've already dealt with this, and it's not necessarily a memory issue. If you understand how it worked in the preliminary work, you really don't have to spend too much time with these formulas. So having said that, what we're trying to get at is we are developing the analytical geometry behind determining what all of the work in chapter 4 is giving us. So the whole motivation for chapter 4 and why do we do all these calculations actually boils down to an area problem. So what we do, and I'm going to break it down a little nicer, I'm interested in finding the area under the curve. And so let's look at, breaking up the curve based on the intervals and making sure, let's say the curve is a nice constant, f of x equals c. Well, if you're going to find the area under the curve, you'd have to kind of understand where to stop and start on your curve. And what happens is it gives you endpoints and it gives you a geometric shape for you to figure out. So you kind of notice that, what shape does this make? And if it's a constant curve, you probably say, oh, that's my favorite shape of all. That's the rectangle. So you guys have a formula for rectangles. We've done this before. Area is always length times width. But if you want to try to relate it to the coordinate system and what's actually the x values and the y values, the length is the distance from A to B. Oops, let's make sure I draw the correct distance. And if you're going to decide what distances look like, remember, that's where we're getting the b minus a from. So that's the length. And the width is the height. So in our case, if we were kind of saying, well, if the width is the height, what is the y value at each of those points? And the y value at each of those points is c. So this is where they're getting this formula from. So, oh, that's kind of interesting. I see the b minus a kind of coming into the picture. Well, what motivates us? Not all these shapes are going to be pretty. You may end up getting a more interesting curve. And so let's say we have a curve f of x, and we're still interested in the area from A to B. So let's say here A, and then we have B. So it still involves, we still have to kind of understand what are the endpoints of the function. But do you notice, I mean, look at the shapes we have here. This is not any recognizable geometric shape from our past. So this is what's going to motivate us. What is the area? And at this point, for this section, what we end up doing is we break it down into something we actually understand. And we try to break up this oddly shaped area into a bunch of rectangles. And sometimes these rectangles overestimate, sometimes they underestimate. But when you find the area of all these little rectangles, they should give you a good approximate of what the area is. So we try to break it up into a formula that we understand, and then we'll kind of see the motivation behind this. So just kind of remember at this point, right now we can approximate the area by dividing it into rectangular regions. And how we do this depends on what do we want to call the width of the rectangle and what side of the subinterval are we going to use to calculate the height? So that's what we're going to discover when we go through the next two examples. And I picked a nice curve, and you can clearly see what the area will be, because you'll kind of recognize you know, very familiar geometric shape. But I want to show you the motivation behind all of this. So without having said that, we're kind of looking at it, example one. It's excitement to have that. So we're going to look at the function f of x equals 2x on 0, 4. And so this is where, and the reason why we were kind of practicing partitioning items into subintervals, because everything kind of boils down to you looking at your x-axis. And see if I can kind of give you this. We should have our x-axis right here. Everything boils down to breaking it up into equal parts so that you can make your rectangles. So when we're looking at number one, in terms of considering this function that we have, if we're looking at the equation only on the interval where x equals 0, all the way up to x equals 4, 1, 2, 3, 4, then you could kind of see if we are creating the shape, you're going to be able to see like, oh yeah, it looks like a triangle. And because it's superimposed on top of a coordinate system, yeah, I can use the triangle area formula and I can get the exact value of the area. But remember, not all of our curves are going to be nice, so I want to give you a technique to use. So we're going to go with something concrete, and then we'll work to something a little more abstract in a few examples from now. So the first idea is us breaking up the distance from 0 to 4 into equal subintervals. And then this is what they're specifying for us. We may have to decide later, but they are specifying that they want to break this up into subintervals of width 1. So what are they trying to tell us? Subintervals? Guess what? That's delta x. So if we play with this, I mean, you can visually see, if we break it up into subintervals of width 1, what do we have? We have a 1, a 2, and a 3 that we're labeling. Number-wise, it's very nice. And if you're interested, you could talk about what's going on with the, how to label your particular values. Now here's where it differs a little bit, and you have to kind of pay attention to what we care more about in terms of our calculations of our rectangles is they want us to list the left endpoints of each subinterval. Okay, so if we're doing this, if we're looking at left, see if I can, keeping in mind looking at left side, start off on the left side, our A is going to be, which our x of 0 is, and the left endpoint, the leftmost endpoint is 0. So if you're kind of thinking about that, right away you can label that as x of 0. And if you label that as x of 0, then you kind of understand, oh, x of 1, x of 2, x of 3, and x of 4. But we only want the left endpoints. And if you're kind of dealing with how many subintervals are we going to have, I'm going to erase this highlighting for a second. Let's look at our subintervals. I have 1 subinterval, 2 subintervals, 3 subintervals. And remember, I'm only looking at the distance from 0 to 4. So there's only 4 subintervals. Don't go crazy. So if you're only listing the left endpoints, then we have A, which is x of 0 is going to be 0. That's fine. The next one, your x of 1. What's your left endpoint? It's going to be 1. X of 2 is equal to 2. And x of 3 is equal to 3. And you realize why we're leaving out the number 4. I mean, I know it's a pattern that we have, but just remember, for making subintervals, the first subinterval from 0 to 1, And I'll even go from here just to kind of show you. From 0 to 1, the left point is 0. Now the next subinterval from 1 to 2, right? That's the next one that I've highlighted. The left endpoint is just the 1. The next subinterval from 2 to 3, the left endpoint is just a 2. That's the yellow interval. And the last teal one, I kind of alternated colors from 3 to 4. The left endpoint is a 3. So we don't include the 4 in our calculations because we're only looking at the left side. Now, what does this mean? This is giving you the motivation on calculating the heights. So when you are looking at the left endpoints, we care about drawing vertical rectangles using only these points. So first off, left endpoint of 0, it has no height. But the left endpoint of 1 has a height of 1, so that we have a rectangle that we're dealing with. See if I can subdivide that for you. I'll draw it a little darker so we can see. Now, if we're making the next rectangle, remember we're looking at f of 2. If we're dealing with this, we should be having this here. So we're kind of subdividing up the intervals. And then the last one is the 3. That's where we're looking at the value of the function. Now, if we draw rectangles, what we're looking at is rectangles are calculated only by the height of their left endpoint. So this is where we want to be careful, because I know you can draw rectangles in any old direction, but if we're paying attention to what we're looking for, if I look at the interval from 0 to 1, the yellow region, there really is no height on the rectangle. What I'm interested in looking at the rectangle from 1 to 2, and see, we would draw it this way because you're using the left endpoint to determine who the height is. Similarly, the next yellow region from 2 to 3, the rectangle would be drawn. Looks like it's a little shorter than the curve. And then similarly, the interval from 3 to 4, the rectangle would be drawn this way. So they're all shorter than the curves. So what you end up having, if we're really looking at this, is we have a rectangle here of height 0, another rectangle, and another rectangle. And sometimes you can color them just so that you can see them better. So if you have an idea of what these rectangles are and what their heights are, we can now find, if you add up the areas of all these rectangles, you have a good estimate of what's the area under the curve. So kind of remember, if you're kind of thinking, what does this mean with rectangles? Recall, rectangles always have the area which is length times width, or sometimes we use base times height. And in each of these cases with the rectangle, who is the base? What is the distance between each equal subinterval? Well, that is delta x. And if we want to look at this a little bit clearly, who is delta x? In our case, with 1. And then if you look at the height of all these rectangles, they all differ, but they are all based on what the function is evaluated at that left endpoint. So what we're looking at is f of x. So h is actually f of x. And now you'll start to see where we're getting our particular formula from. Okay, so, and I should probably be a little more specific, and I will be. Delta x is for sure just the number 1, but f of x may change based on which endpoint you're picking. So I will be even more specific. and shut off my video. There we go. There, you guys saw my hand. I'm going to be more specific and look at, see if I can find the red pen again. The fact that you're choosing different x values, so we're going to call this f of x sub I. So that's our counting. So basically, the area of the rectangle is delta x times f of x sub I. So 1 times f of x sub I. And you're probably guessing, oh, with those i's, we are going to calculate them based on how many rectangles we have. So here we go. Now here, you're going to see the notation. I call this L sub 4. What do you think L stands for? You were right if you said left. And so the subscript stands for how many rectangles you're drawing. And then the L stands for the fact that you're using the left endpoint to calculate the height. So if I can kind of give you this, without a formula, you could ignore the delta x issues. But without a formula, I can say, hey, the first rectangle from 0 to 1. Well, the base is always 1, but the height is 0. The second rectangle, that's the next teal one. The base is always the distance of 1, but this time the height, we can kind of see where that is. The height is the function evaluated at x sub 1, and that's equal to 2. We can see that on the graph very nicely. The third rectangle, the one that has the subinterval from 2 to 3, well, the base is always 1, but if we want to talk about the height, we have to look at the left endpoint, and then that would be the function evaluated at x sub 2, and so that ends up being a 4 in this case. And I'm going to move this over just a little bit, so we have a little bit more room. And then the last rectangle, that is the subinterval from 3 to 4. The distance of that base is still 1, or the length of the base. But if you want to find the height, you have to go to your graph and see, oh, okay, that's going to be marked off where the f of x sub 3 is. In that case, it's equal to 6. So visually, you can calculate areas of rectangles, no problem. Please let me insert the math notation to help you out a little bit, just in case we end up using it again. So keep in mind what we do. What does the 1 stand for in each of those cases? That's the length of the subinterval. So we should have delta x. Now the 0, the 2, the 4, the 6, that is your function evaluated at your left endpoint. And I can be a little bit more, I'll do numbers for you just to help you out. Subscripts to help you out. So x times f of x sub 0. Miss that delta x, be careful. Sometimes being left-handed is a disadvantage when you're dealing with these. You guys will notice weird things pop up. So I am looking at the second rectangle. If you might want to see if I can kind of highlight where I'm kind of alternating. That might be helpful. How am I getting that height of 2? Just kind of re-emphasizing that is the function evaluated at x sub 1. And then I still have the delta x. How am I getting, let's make that delta a little bit more proper. How am I getting the 4? That is the function evaluated at x sub 2. And how am I getting the 6? I still have delta x. That is the function evaluated at x sub 3. So now I'm hoping that you're kind of seeing the fact that there's a reason why we're using x sub I. It depends on what endpoint are we using to calculate the height. You want to be a little more clearer. And I'm just translating this to formula. And of course, we can deal with numbers if we see this. I mean, you don't have to write all this down. And I just think it's nice to develop. So if we end up having generic ideas, you'll see what's happening. What was f of x sub 0? That's f of 0. f of x of 1 is f of 1. F of x of 2 is f of 2. F of x of 3 is f of 3, only based on the subintervals that we were doing. So that's generic speak to help you out and understand why are they getting all these delta x's and f of x of i's everywhere. It really just has to do with base and height of each of the individual rectangles. So you don't need this to do this problem. So let's just kind of move forward. And I'll still develop this just so that you get used to the notation. Okay, so what happens when you say what's 1 times 0? We have 0. 1 times 2, 2. 1 times 4 is 4. 1 times 6 is 6. And again, I'm just going with the areas of each of the individual rectangles with the particular sub interval that I've highlighted. Well, let's add all those up. Not too hard, right? 0 plus 2 plus 4 plus 6, that's 12. You want to be a little precise. Are we finding areas? So we need to say square units, just to be careful. Now, if we're going to inspect and you're kind of looking at what are these rectangles doing according to the curve? Are they finding the exact area under the curve? And the answer is no. Look at what the rectangles are doing in relation to the curve. Each of those rectangles appear to be smaller than the actual curve itself. There seems to be some empty space in there. So what we're trying to say when you use the left endpoints in this particular situation with this particular function, by inspection, L4 is an underestimate. And it's kind of important for you to see this. What does this mean? The rectangles that you're making are a lot smaller than the curve that you see. There's empty space that you have not accounted for. If you want to be more mathy, you can say this as L4, the sum of the areas, is actually less than the area of the actual. And if you are interested, by the way, I mean, I know I kind of mentioned it. We could actually see what's happening. Let's look at our triangle one more time. If you translate this triangle, we want to talk about the area of the actual triangle. The area of the triangle is what? Base times height divided by 2. Well, if you translate this triangle to just numbers, okay? And let me move this just a little bit. Move this up here so you guys can all see. So I have the area of the actual, I have an actual formula for this one. If you actually draw this triangle, you notice, just by looking at the distances, you have the distance between 0 and 4, means that the base is 4 units. And if we actually look at the height, the actual height of the triangle is over here. So that's 8. So if we're kind of looking at this, the area of this triangle is 4 times 8 divided by 2. So what is that, 16? And it's 16 square units. So if you actually now compare number-wise, if the area of the actual is 16 square units and your estimate gave you 12 square units, now for sure you verify, oh, you have an underestimate. And it's really nice to see when the curves are nice and they give you proper geometric shapes. But the idea is for you to recognize what type of rectangles you are making. And if those rectangles are falling below the actual curve or above, and that's a really key idea that, oh yeah, it's an underestimate because the rectangles are obviously smaller than the curve. So don't let the notation scare you, just kind of really look at your picture. So that's great, it gives us an estimate. What we're kind of looking at here, let me look at the other side in a sense. So same type of problem with example 2, but this time what they want us to do is deal with the right endpoints. Okay, so subdivisions, still okay. We're still going to do the same idea. They are telling us that they already know who the delta x is. It's equal to 1. And so we're still looking at the interval from 0 to 4. So we have 0, and then 1, 2, 3, 4. And we'll still look at making the subdivisions or the subintervals. So if again, if it's with 1, then you are marking what's happening at 1, 2, and 3. And so if we do this, you can kind of see if you feel like it, if you want to name off your subpoints. What do you have? X sub 0, x sub 1, x sub 2, x sub 3, x sub 4. Now, remember, the idea is to find the area of the actual curve, underneath the curve from the x equals 0 to x equals 4. But we have to be extremely careful because they want us to look at the right endpoints of each of these subintervals. And so remember, if I'm looking at the subintervals, I have a subinterval from 0 to 1, 2 to 3, and I'm just alternating colors so that we can refer back to them later. And if you're going to be playing with the right endpoints, this time around, you would be listing not your A, but you'd be listing x sub 1, which is equal to 1. That's your right endpoint. X sub 2, which is equal to 2. X sub 3, which is equal to 3. And this time you're using x sub 4, which is equal to 4. So it's the right point in each of those colored intervals. And if we're working through this, what are we ending up doing is we're drawing rectangles based on this right endpoint. So if I can, let's kind of maybe mark them. If I can mark them maybe in, I don't know if you can see them in green. The right endpoints in each of the intervals are now right here. And if you want to create the rectangles based on this, they're going to give you the height based on this. So my vertical rectangles that I draw right now, it's going to be calculated using the y value associated with these right-handed endpoints. Okay, so I'm trying my best to draw this vertical line to help you see the rectangles that I'm drawing. And when you make the rectangles this time, you kind of see that we would be drawing them, and they're going to look something like this. So now, if you kind of compare to drawing the rectangles using the left endpoints versus the right endpoints, the right endpoints seem to not have any empty space anymore. What we end up having is we're over our curve. And then you could probably guess visually what's happening. But just so that you see what's happening, if we're going to look at the sum of all the areas of the triangles, rectangles to make the triangle, excuse me, you've probably guessed it. If you're using right endpoints, look at R4. That is telling you that you're using the right endpoints of each of the subintervals to calculate the height of the rectangle. So what does that look like? Just if we use numbers, the first one, if I'm looking at the first yellow region from 0 to 1, the area of the base is 1, and then the height this time is 2. That's where we're getting our height right here. 2. Add that up to the first teal subinterval. The area is base, still 1. The height of this one now is a 4. Move on over to the subinterval, that's the next yellow one from 2 to 3. The base is still length 1. This time the height is at 6. And the last one, subinterval from 3 to 4, the base is still 1, but this time the height is 8. Let's write that a little nicer, the 8's up here. So we can visually do this with numbers. You don't have to really think about notation, but I would like to show you what it looks like with delta x, f of x of I, so that if you see this notation later, you don't freak out. So just so that we are seeing this. You know, each of these ideas is we have delta x, and then where did we get the 2 from? It's actually the f, the function evaluated at 1. Where do we get the 4 from? Delta x, the function evaluated at 2. Where did we get the 6 from? The function evaluated at 3. Where did we get the 8 from? The function evaluated at 4. And if you want to be precise, and you want to say, well, what does this mean in terms of all the subscripts of the x's? Well, here's your notation, delta x, f of x1 plus delta x, f of x2 plus delta x, f of x3 plus delta x, f of x4. And that's all great. I'm just trying to get you used to this. Notice who you chose. The x of 0 was never part of your calculation. And you could compare this back to the example 1 and see that, oh yeah, we never used x4 in example 1. So yeah, interesting. So having said that, we could just do the calculations. 1 times 2 is 2, 1 times 4 is 4, 1 times 6 is 6, 1 times 8 is 8. We add all this up, and we should get 20 square units. And then by inspection, when you made all your rectangles, all those rectangles appear to be bigger than the curve. So for sure, we've got ourselves, R4 is an overestimate. If you want to be nicer, you can say, well, notation-wise, R4 is always bigger than the area of the actual. If you guys remember what the area of the actual was, let's go back and look. We found it earlier. You say, oh yeah, the area of the actual was 16 square units. And we ended up getting, we got 20 square units. So we get overestimates, we get underestimates. What I'm particularly interested in is sometimes the left endpoints, the right endpoints don't always do the job. They end up being a little bit more not so exact. You're either really overestimating or really underestimating. And so we kind of can probably guess the actual area is somewhere between the left endpoint and the right endpoint. And we've already done this with the geometry part. Remember, we found out that the area was 1/2 base times height, which is 1/2 4 times 8. And we had gotten the 16 square units. And so when we're kind of looking at our notation math-wise, the 16 square units is in between the 20 and the 12 that we got. And if you are using math notation to talk about L4 and R4, 12 was L4. The actual area is in between L4 and R4, and we've kind of developed that. We actually see that it has to be geometrically and then physically when you're looking at the analytical part. So if you are interested, the idea is if we, instead of using maybe 4 rectangles, maybe we use more rectangles, we're going to get a little bit more precise of a rectangle and a more of a precise area. So if you're interested, and I'm going to just start you off just so that you can see what's happening. If we break up, again, the interval from 0 to 1, 2, 3, 4. Okay, so if we break this up, not into sub-intervals of length 1, but this time sub-intervals of length 1/2, and then find L8 and R8, what you are now doing is breaking it up into 8 rectangles. And so just to get you started, I'll let you develop this on your own so that you can actually see how close you are getting to the area. But the idea is the more rectangles you can make, the closer you're going to get. And if you're interested, remember, if the subintervals have length 1/2, just kind of keep in mind that you'll be now looking at, if it will let us, here we go, all the numbers in between here and here. And so if we want to make generic, what do we have? X sub 0, X sub 1, X sub 2, X sub 3, X sub 4, X sub 5, X sub 6, X sub 7, and X sub 8. So we're going to have a bunch of different heights. And depending if you're going to use L8 or R8, the rectangles will either be an overestimate or underestimate. But play around with it, see what you get, and see how close you get to the actual area. But I'll move on. Sometimes you might be interested in pausing and trying it on your own so you get an idea. And then you also might be interested in what happens if it's a curve that's unable to produce a nice geometric shape like the one we just did. And that's kind of our motivation behind all of our calculus here. So we have ourselves a function. And this time they tell us what it is, f of x equals x squared, and yeah, it looks like a parabola. And they want us to use L4 to approximate the area bounded by f of x equals x squared, y equals 0, and x equals 0 and x equals 1. Okay, so they didn't specifically tell us what this means, so sometimes if you're thinking about it, you have the area bounded by the curve, f of x equals x squared. Now y equals 0 is the x-axis. So you're bounding it by this curve. And x equals 0 is the x-axis. Oh, excuse me, I should say y-axis. That's x equals 0. And x equals 1, if I can give a little bit more, I'm going to space it out just a bit more. I'm going to put the 1 over here. So x equals 1. So what we're really looking at is the area. It does kind of look like a triangle, but it's a little bit curvier on the top. The hypotenuse is not really a hypotenuse, it's a curve. So a lot of times it helps to understand what you're bounding everything by. And once you understand that, then you kind of say, well, what am I supposed to use? What does L4 mean? First off, subscript. 4 rectangles. And the L means that the height is going to be calculating as the left endpoint of each subinterval. And so it's very important to know that notation. They're going to use that a lot in your homework. And what's interesting is as you're looking at this picture, now that we kind of understand the area that we're using, I'll erase a little bit so that we can mark our graph a little nicer. If we're looking at the x equals 0, x equals 1, they are telling us our left endpoint and right endpoint of the entire interval. So that means x equals 0 is over here. And I exaggerated so that we can see what's actually happening. So I'll kind of maybe look at that later. So we're looking still at that area. So now that you know the left endpoint and the right endpoint, they didn't specify the width of the subinterval, but you can figure that out by notation and calculating the delta x. So what does this tell us? Delta x is always going to be b minus a divided by your n, which is 4. And what do we have? B minus a. B is 1. A is 0. So that should give us our rectangles have base 4. So, not base 4, base 1/4. And that would make sense if you are breaking up the interval into 4 equal rectangles. You guys are, you know, fractions. Halfway is half, 0 and 1. But if you want 4, we should be seeing 3/4 right here, and then 1/4 right here. So you kind of already know the numbers geometrically wise and from your past dealings with fractions. So I kind of use that to help me out. And then also, if I am using L4, it might be convenient so that you're kind of listing who your subscripts are. So left endpoint x0, x1, x2, x3, and x4. The left endpoints of each of the subintervals, sometimes it helps to kind of point them out. Pick all the left numbers, and that's who we're going to be using to calculate the heights. So you can draw the picture to help you. If you're interested, I have 0. I'm not copying and pasting, be careful, there's my left hand again. I have this happening. I have another height that I'm going to be dealing with, another height that I'm going to be dealing with, and another height that I'm going to be dealing with. So those are the heights that I have to look at. And when I'm dealing with drawing my rectangles, that's what's determining the height of my rectangles. And so you could kind of see now we have our rectangles in mention as well. So if you'd like to, just so that you see the generic formula, if I'm calculating L4, it's always base times height. So if I'm using some of the function notation, the first endpoint I'd be dealing with is x of 0. So base times height, that's the first rectangle. Second rectangle, base times height, that's f of x sub 1. Third rectangle, delta x, base times height, f of x sub 2. And fourth rectangle, base times height, delta x, f of x sub 3. And then if you're now playing with this, we can do some calculations. Delta x in each of our cases is 1/4. And so our job is to plug in, and actually I'll be a little more precise for you. X sub 0 is 0. So we have f of 0, 1/4. X sub 1 is 1/4. X sub 2 is 1/2. And x sub 3 is 3/4. So you see all I'm doing is replacing my labels with my actual x values that I've chosen. And then now you're using function notation to compute your heights. And so these are not so nice. Well, they're okay. You got f of x equals x squared. So remember, if f of x equals x squared, each of your heights are going to be found by using the function value. So if f of x equals x squared, f of 0 is 0 squared. f of 1/4 is 1/4 squared. F of 1/2 is 1/2 squared. F of 3/4 is 3/4 squared. And if you want to calculate this with your particular function, you kind of notice delta x. Did I just use delta x? I actually have numbers for delta x. That's 1/4. If you're interested, you could say, oh yeah, I see 1/4 everywhere. Why don't I factor that out? So then all I'm left with is the 0 squared, which is 0. The 1/4 squared, which is 1/4 times 1/4 is 1/16. The 1/2 squared, 1/2 times 1/2 is 1/4. And the 3/4 squared. 3/4 times 3/4 is 9/16. And so now it's a matter of us adding our fractions. And if we do that, maybe we pull up our TI because we have a lot of brain power we have to worry about. 1/16, I mean, not too bad. What, 10/16 plus 9/16. Let's pull up our TI. Our brains have to deal with so much. Let's kind of use our strengths to deal with some of the more complicated stuff. So again, let me look at this one more time. We have some stuff from our past. I'm just looking at adding fractions. I have 1/16, 1/4, 9/16. Okay, just double checking. 1/16, 1/4, 9/16. Sometimes if I'm switching back and forth, you can turn that into a fraction if you're interested. And we should get 7/8, but that's only the sum of the inside. Let's make sure. So we have 7/8 is the sum of all those fractions in orange. And so at the end, if we're finding our actual answer, what should we get? We would have 7/32 square units. Don't forget the fact that your units are square. And just by inspection, did you make an underestimate or an overestimate? And you can see right away, oh yeah, there's empty space between the rectangles and the curve. So a little note to remind yourself is that your L4, which is equal to 7/32, that should be less than the actual area A. But it's a good estimate. And if you're interested, another way to make this a little less painful, as sometimes the curves get really, really complicated. If you want to use some of the tricks we used in 3.8 with calling up the y variables in your function to help you go through these problems, it might be beneficial so that you don't get really tied up on some of the computations. So just kind of a heads up if you're interested. A little note, if you wanted to use like your f of x of i's, you're trying to calculate those, and this one's not so bad, it's f of x equals x squared, but you can either use your table and your TI, which gives you another version, or the variable feature in your TI. So remember we talked about that a couple sections ago, where once you enter in y1, what's it? y1 is equal to x squared. Then what happens is you would choose y variables. Oops. Then we'd have to go with what entering function. And then we can pick y1 to help us go through this. So what would that look like once you have everything set up? I don't know if you're interested, my L4 would equal, I factor the 1/4 out, make my life a little easier. So that would be y1 evaluated at 0 plus y1 evaluated at 1/4 plus y1 evaluated at the 1/2 plus the y1 evaluated at the 3/4. Sometimes that saves a little bit of time and you can see what works out. And it also could kind of give you a quick way to figure out R4 if you're interested. And it's okay, whatever works for you. So feel free to explore that to get yourselves maybe a little bit quicker way to find your L4. I still recommend kind of showing the setup because it's very easy to switch off and get confused as to who to plug in. So I would at least kind of show, I'd be looking at maybe at least showing this version just so that you're clear on who you're plugging in and maybe around here. But again, you go with what is more comfortable with you. And if you're interested, what we can do is let's look at something with a trig function, a little more exciting. And example 4. So same idea. They're using R3 to approximate the area bounded by the function f of x equals cosine x, the x-axis on the interval pi/4 to pi/2. Now, feel free to graph it and see what works, but I kind of want to show you that you don't have to actually see the picture to understand what is going on. First off, if we're looking at what does it mean to be R3, that's telling us n equals how many rectangles? It's 3. And if you're trying to talk about the height of the rectangle is the right endpoint for R of each subinterval. So if you want to get a picture of this, you don't have to draw your function. Let's draw a quick number line really quick. And keeping in mind, you already have your interval. So we have pi/4, left point of the full interval, and pi/2, the right endpoint. And so, yes, that gives us who is A and who is B. But if you're kind of using x sub 0 or x sub I notation, think about it this way. We're breaking it up into 3 rectangles. So what we would do is just break this distance up into 3 different pieces as best as we can. So we already kind of know what we're dealing with. We should have x sub 0, x sub 1, x sub 2, and x sub 3. And if you're looking at these numbers, who would you be calculating? It's the right endpoint of each subinterval. So if I can highlight them, I have 3 different subintervals. Who would the right endpoint be? In the yellow subinterval, we have x sub 1. The right endpoint in the teal subinterval is x sub 2. And the right endpoint in the pink subinterval is b, pi/2. So those are kind of the numbers that I should be plugging into my function. And if you want to figure out what those numbers are, that's where we're going to deal with our delta x. Well, delta x can always be found by subtracting right endpoint minus left endpoint over the number of rectangles that we want. So in our case, it's pi/2 minus pi/4 all over 3. So a little fraction work, pi/4 divided by 3, we actually end up having 1/3 times pi/4, pi/12. So now you can actually figure out those values, and if you want to, sometimes it's really helpful just to help you out with numbers. Just write it out. Sometimes if you do mental math, I've seen so many minor math mistakes in calculus 1. I don't want you to have to suffer, so just take your time, write it out. So x of 0 is still pi over 4, but if you want to look at who x of 1 is, it's pi over 4 plus a pi over 12. Well, have a little fun with fractions, feel free. You can find the common denominator, or you can say 1/4 plus 1/12 on your calculator, not forgetting your pi at the end. You should have pi over 3 when everything reduces down. So I got that marked. And if I want to find who x of 2 is, what am I doing? I'm either adding on the delta x to what I just got, or I can say what? Left endpoint plus 2 times delta x's, which in our case, delta x is pi over 12. I mean, with concrete numbers, it really doesn't matter. So whatever works for you. So we have what, pi over 4 plus pi over, well, we have pi over 2 12s is pi over 6. I should check. It's right around this time, my brain gets tired too, so I'm going to double check with this. And so pi over 4 plus pi over 6, I'm just going to say what's 1/4 plus 1/6 on my TI. Going to convert it to a fraction, and yes, we're going to get 5 pi over 12. So we have 5 pi over 12 for our x of 2. We already know who x of 3 is because that's the endpoint of the interval, but if you would like to verify, be my guest. But remember, what y values will we be calculating? F of pi over 3, 5 pi over 12, and pi over 2. See how I marked them as the right endpoints of each subinterval. So now we want to take this and have the calculation. I'm going to use generic formula. R sub 3 is calculated by delta x times your function evaluated at x of 1 plus delta x plus your function evaluated at x of 2 plus delta x times your function evaluated at x of 3. See how we're taking all the right-hand endpoints. If you're interested kind of simplifying the algebra, you end up seeing the f of x of 1, f of x sub 2, and f of x sub 3 if you factor out the delta x. Saves a little time. And so now I know who is delta x. That is pi over 12. And this would be me. The next step would be to see if I can figure out who am I plugging in. Who is x sub 1 in our case? It's pi over 3, according to my marking on my x-axis. I'm going to add that to the function evaluated at pi over 12, that's x sub 2, plus the function evaluated at x sub 3, that is pi over 2. And so this is kind of where, sure, the cosine, it's only f of x equals cosine x. You can definitely do this by hand. But again, I'm really interested in, let's use our TI and let's see what we can do with that. So what I would do with my TI, sometimes it's going to save us a lot of time. First off, enter in y1 into your function editor. So who's our function in example 4 is f of x equals cosine x. Cosine x. And I haven't used my calculator in a while. I'm gonna double check my mode really quick. Sometimes if you switch off between degrees and you forget, remember everything here is in radians. So let's go to mode and see how I was in degrees earlier. So let's change everything to radians. That sometimes throws us off a bit. Check one more time because I'm paranoid. Yes, we're in radians. Okay. So now, you could actually take care of this all in one shot if you're interested. If you want to calculate this, we are going to look at pi over 12, and I'm paranoid, so I'm going to put everything in parentheses, pi over 12. That's me factoring everything out. But now I'm going to add this to my function evaluated at pi over 3, 5 pi over 12, and pi over 2. So how do I get that up again? We're going to press the variable key vars. Scroll over to yvars. Select function. Now you got y1. We already entered it in, but you're saying y1 evaluated where? And that's where we can say pi over 3. Close the parenthesis. You're adding that to y1, so vars. Scroll over to yvars, select function, select y1. This time, you're plugging in 5 pi over 12. Cool. One more. Let's get this vars, yvars, function, still selecting y1. This time we're plugging in pi over 2. And I know you probably could have done that one. That one's a nice one without it. But like I said, save your energy for the actual calculus. Okay, so that is what we just set up. You press enter on your calculator. You end up getting a decimal. That's because pi over 12 is not a special angle. So you don't get something exact. So we can approximate. And depends on how much they ask you to approximate to. I always do rule of thumb. If not asked, I always take 4 decimal places. So if that's the case, it should be 0.1987. We'll go back, record my answer. And if we're doing that, it approximates approximation from the TI 0.1987. And don't forget, you're actually looking at square units because you're approximating the area. And so the question would be, just so that we're clear on this, you know, what if they asked for L3? So kind of what I look back and look at what endpoints I'd be using, just kind of draw a quick sketch of what you see. What do you have? Pi over 4, pi over 2. And then you have your subdivisions, pi over 3, 5 pi over 12. And if you're kind of looking at your subintervals that you're making, just so that you can see. And then if you're interested, x0, x1, x2, x3. If you wanted L3, what are we using? What endpoints? L stands for left. So you could kind of mark them, what you're looking at. So you're saying the yellow one, the yellow subinterval, I'm going to use x of 0. The teal subinterval, x of 1. The pink subinterval, 5 pi over 12. So we'd be using x of 0, x of 1, and x of 2 to calculate the L3. So sometimes, like I said, you don't really need to draw all of the rectangles. I know some in WebAssign, they'll make you practice a lot, and it's really good practice on that. So feel free, play around, and see where you land. See how you're feeling about it after you do a couple more practice ones. So if I can kind of give you a summation of all of this, no pun intended, I'm using the summation notation. Anyways, you have the general estimates of the actual area. It kind of helps you understand what endpoints you're using. But again, I don't bother memorizing things really if I can automatically draw them and visualize them. Save your brain for other things. We've done a lot of left endpoints. We've done a lot of right endpoints. The only things we have not done, but I think you'd be able to figure out without me, is you will see M. And if you're interested, what does that mean? What do you think? Well, left, right, M, middle. Yeah, this is actually midpoints. And so each of your x of 1 so this time they don't want to call it x1, x2 because they're not really in your intervals. They denote this by using asterisks asterisk. It's very hard for me to say. But these are the midpoints of each subinterval. And so they really don't have a way to denote them because you've already listed your subinterval left and right endpoints as x0, x1, x2, and so on. So just a quick picture so you can understand this. And I know you could catch on, so you don't need me to explain it. But what's happening is, let's say you have your, let's draw it a little higher so that you can see this. Let's say we have our A and our B, and let's say we have 4 of them, just so that we can tell. So we would end up saying, okay, that's no problem. A is x sub 0. Then B is x sub 1, 2, 3, 4, x sub 4. So then we have x1, x2, x3. Now, if we're dealing with the midpoints, what are they looking at? It's not x0 or x1. They're looking for what's happening here. Let's do this in red. So that has nothing to do with the actual original notation. So this is why they kind of denote them as, well, that's kind of like the first subinterval. So that's why we'll call it x sub 1 star. That's like the second subinterval. So that's like the x sub 2 star. That is the third interval. That's the x sub 3 star. And then the fourth interval is the x sub 4 star. So that's why they're using the star notation, because you're not really referring to the original endpoints left and right. How do you calculate a midpoint? Remember, you're just taking the average. You want to play with that? What do we have? For instance, x sub 3 star would be the sum, x2 plus x3, divide by 2. So average, finding the midpoint. And you've done that before, but feel free to explore that. There's a couple problems in your homework. And I have a feeling if you could do left and right, midpoint's not too big of a deal. So we are almost there, everyone. I really like going over the actual examples with concrete numbers and concrete functions so that you could understand the point of everything. But eventually, the idea when you are drawing these subdivisions and subintervals is the idea is for us to take so many rectangles that the rectangles that we draw end up being the actual area under the curve. So we don't end up having empty space like we see in example 3, or we don't have overestimate like we saw in example 2. So feel free to look at your textbook for those cute pictures. I can't give you everything, right? You gotta look at some things. But the idea is behind this, and this is what I mean by a lot of rectangles. Emphasize, a lot. You can actually define the area under the curve to actually be a limit as n approaches infinity. And so that's why they mean by a lot, like an infinite number of rectangles. The fact that you're slicing up the curve in such thin slices that all of those heights end up being the actual, to fall under the curve. So what we end up having is the limit definition of area. And you're like, oh, I thought limits were disappearing for a while, and nope, they come back. So big deal. That's why we were big on limit notation all throughout this class. We have limit notation. They're saying as n approaches infinity, ideally, if you have an infinite number of rectangles underneath your curve, your area will actually equal the limit of that summation of all those areas. And so that's what they're trying to see with this notation. So remember how I was using the f of x of I delta x? Well, we finally have arrived now. So when we're going to do the next few problems, before you even jump into calculating the limit, the first thing to do is set up everything just like we were doing earlier, but we're doing this in terms of delta x and f of x sub I and a plus I times delta x. So all those formulas kind of come back into play. So I have the recipe. I definitely want to walk you through the process so that you can kind of see where my thoughts are going. And yes, we will be looking at using a lot of limit notation, so you cannot drop limits off until you've actually evaluated. And you will see that this is where people like walk into the classroom and they get really intimidating because you've got a lot of math symbols going on the board. So good to impress your friends with. So just so that I could help you out, we already kind of went over computing how to find delta x. And even with delta, x of I, we found out that it's the first endpoint plus however many delta x's you wanted. So we've kind of played with that. Computing f of x of I is using function notation. I'll walk you through that, don't worry. And then when you are computing f of x of I times delta x, all you're doing is taking step 3 and multiplying it by delta x when you're done. And the whole idea of this part, if I can highlight it, see where it's located in the limit definition. We're plugging this in. So plug it into the limit definition. And whenever you plug it into the limit definition, what's going to happen is we're going to have to end up simplifying. And so we're coming full circle from everything we've done since chapter 1 until today. Usually when you're simplifying the limits, well, you see that summation notation right there? Eventually, what's going to happen, this involves, as far as the simplifying is happening, we end up using some of the formulas for the summation of a constant, the summation of I, the summation of I squared, the summation of I cubed. Remember those formulas we went over in the preliminary work? That helps us with the simplifying, and also, we invoke Bill Gates again. Bill Gates' principle. I should probably spell that right. It's principle. There we go. Or what is that, dominant term analysis? That's kind of the more mathy way. So that your teachers don't yell at me later. That's going to help you actually calculate the limits. So having said that, let's demonstrate a few, get you used to that. And once you do this, you might start asking, like, there's a lot of things going on. Is there an easier way? And yes, there will be. And I will share that with you. Just keep you on the edge of your seats. Maybe we'll see that in the next section. But I have a few more examples to play with. Even though it seems kind of long, I think it's necessary to walk you through each of these so that you could kind of see what happens if any tricks are thrown along your way. And then I'll end up with the application so you can also see how that works too. So, you know, if you feel like you need to take a break at this moment, totally fine with me. You just press me on pause, I won't know. And then come back refreshed because we have a lot of algebra also to incorporate into our calculus. So, example 5, they define who our function is, f of x equals x squared. And we are looking at this on the interval 0, 1. And they want us to, and be careful, they are specifically asking us to use the limit definition to find the area under the curve y equals f of x. So we're going to do some setup first before we calculate the limits. So remember, I'm going to use those 4 steps we approached earlier. So first things first. I want to calculate who is my delta x. And so remember delta x, I have my formula, subtract the endpoints, right minus left over n. And remember, they gave us the interval and they gave us technically who A is and who B is. So we actually have, in our case, our delta X is B is 1, A is 0, and N. See how they don't tell us how many rectangles to make? It's an infinite amount of rectangles. So that's why we can't just get a number. So we just simplify it as much as we can. We have 1 over N. So yes, your delta X will involve N. Okay, second setup before we jump into limit definitions. Next thing you want to do is calculate X of I. So remember, it's always your left endpoint and you're adding on I times delta X because you don't know how many. You want to make that delta a little bit more triangular-like. I try with my crayon. So who is A for us? It's 0. We already know what I is, but delta X is 1 over N. So I'm plugging that in. So what do we end up getting? It's I over N, simplifying a little bit. Okay, moving forward. Now we're gonna look at function notation and compute what f of x of I is. And so what I like to do, just so that you kind of have an idea, is you have an idea who f of x is. In our case, f of x is x squared. So function notation tells us that we would be squaring whatever the x of I is. Well, who did we count for, or who did we calculate for x of I? It was, and maybe I'll just be, I'll give you another step just in case. I have x of I squared. Well, x of I squared, x of I is I over n. And if you want to calculate I over n squared, what is that, I squared over n squared? So you're just kind of using some things to clean things up before you even use limit notation. And one more item, everyone. We got to actually now multiply what we just found, f of x of I, and multiply it by delta x. So what did we just find? F of x of I was I squared over n squared. Who's delta x to begin with? 1 over n. So what do we end up having? F of x of I is I squared over n cubed. So you really have to understand those steps before you proceed. So if you have any issues, please stop. Please really go through them and ask questions before you jump into calculating the limit. Okay, now we are ready. So preliminary work I still find useful. This is great scratch work. Do not think that you want to throw this away. Showing your computations, if you make a little mistake there, then it kind of proceeds to kind of cause issues with the actual area. So you would end up having to look at partial credit and stuff. So please write all of this down. But having said that, if we are using the limit definition, let's write it out in general. The area is the limit as n approaches infinity of the summation of I equals 1 to n of f of x of I times delta x. Okay, so writing that out, the whole reason why I took all those 4 steps is because we can now write in f of x of I times delta x. We can now substitute this directly into our summation formula. So where was that? That was right here. So we still have the limit. You cannot get rid of this. Summation I equals 1 to n. F of x sub I delta x is actually I squared over n cubed. So having said that, we have to kind of look at some of our work from summation notation. Remember, if your variable inside the summation notation is not dealing with your counter, for example, your n cubed, right there. That has nothing to do with the I. So what you can do is you can factor the n out of the summation notations. So that's kind of the next thing. So we have limit as n approaches infinity, and see what I'm doing right here is I'm pulling out, I can't just take the n cubed, it's n cubed was in the denominator, so I need to say it's 1 over n cubed. And that is multiplied by the summation notation of I equals 1 to n of, now we're just looking at I squared. So kind of in mind, if you want to write a note right here, what did I just do with this step? I factored any n's out of the summation notation. A nice little technique there. So now what we do is we say, wait a second, we have a sum of a square, and we have a formula for that. So instead of continuing to use the summation notation, you can get rid of summation notation by understanding what is the sum of a square, or all the numbers squared. And you may want to note off to the side, summation of I equals 1 to n of I squared. We kind of look at this a little bit better. What is that? N times n plus 1 times 2n plus 1. All over 6. So that's why we kind of have to have these down. We have to memorize them a bit. And it doesn't go away, guys. You see it again when you deal with series in Calculus 2, so it's not a bad idea to just have it down at this point. So I'm going to replace all of this with n times n plus 1 times 2n plus 1. All over 6. And let's not be lazy. Please take time to write out the limit notation and your whatever was originally there, the 1 over n cubed. Please be careful, because the minute we skip steps here, we miss something and we have some issues. So at this point, what we can do with this limit notation is that you can kind of simplify the factors of n. So you kind of see you have an n in the numerator as a factor. It can divide out with one of the n's in the denominator. So just so that you see this a little bit prettier, writing this over again, we will end up getting n plus 1 times 2n plus 1 over 6n squared. And now you kind of notice, again, if you type in n going to infinity, you're going to have infinity over infinity. That's the indeterminate form. And so this time, maybe in Calc 2, you can use L'Hopital's, but right now, we're going to invoke Bill Gates. Or dominant term analysis, I should say. And so if that is the case, what we do is we take the leading term. So we're taking the limit as n approaches infinity. And what we're dealing with the leading terms is n times 2n gives us 2n squared. And we still have this 6n squared in the denominator. Well, now, this allows us to divide out. What do we end up having? 2n squared over 6n squared. Well, that actually divides out to just a constant. So that is 2/6. And technically, if you want to be more proper, you have the limit as n approaches infinity of 2/6. But the limit of a constant is just the constant itself. So you end up having 2/6, but you like to reduce usually. So 2/6 is 1/3. So your final area is 1/3 square units. Isn't that beautiful? Look at all that. So just remember, there's preliminary work. Once you have the preliminary work, it's a limit of a summation. And usually it involves factoring out the n's so that you can utilize one of those formulas for some sums of constant, a sum of a linear term or a sum of a square or cube. Once you can replace that into the formula, it's all limit calculations. So a little more excitement coming your way. We're going to move on to something a little more complicated. I know they don't look, the functions themselves don't look terribly complicated, but the limit notation you end up getting could cause some issues. So we'll walk you through this. We're going to look at the f of x equaling 2x plus 1, this time on the interval from 0 to 2. And once again, using the limit definition to find the area under the curve. So preliminary work, everyone. Step 1, calculate who delta x is. Delta x is the b minus a over whoever n is. In our case, it's 2 over n. Step 2, come up with the formula for x of I. X of I is always the left endpoint plus I number of delta x's. And we already know who delta x is, so we have I times 2 over n. And so that will give us 2i over n for our delta x. Step 3, calculate the function evaluated at f of x of I. So again, the function itself was 2x plus 1. So function notation for f of x of I, it's 2 times x of I plus 1. Now we know who x of I is. It's 2i over n from the above step plus 1. And simplify a little bit, where we have 4i over n plus 1. Now, we're going to look at calculating f of x of I multiplied by delta x. So this is 4i over n plus 1. Now when you multiply it by delta x, remember delta x was 2 over n. So be careful. This is a binomial times a monomial, and it's to your benefit to distribute first and simplify. I think that if you try to do that within the limit formula, there's already so many other things you're thinking about. It's a possibility to make a minor mistake. So we simplify. 4i over n times 2 over n. That's going to give me 8i over n squared. Now 2 over n times 1, we have plus 2 over n. So we have a sum this time. So now we are ready. Let's take this. Let's use that limit definition. And again, I'll rewrite it. The more I rewrite the generic definition, the more second nature it appears for me. And that way I'm not struggling to remember it when I take a test. So the limit as n approaches infinity, summation I equals 1 to n of f of x of I times delta x. Now keep in mind, what we're looking at is we need to replace f of x of I, delta x, with the calculation we already used. So let's do that. Limit as n approaches infinity, keep the summation I equals 1 to n. This time we replace it with, it's a sum, so it's 8i over n squared plus 2 over n. And now, what we need to do, remember, we have a sum inside the summation. So one of the properties of summation, I mean, you probably haven't utilized it since pre-calculus, but if you have a summation, what it allows you to do is you can take the summation of each of the individual terms. So you have 8i over n squared, and then the summation that we're plus, summation I equals 1 to n of 2 over n. And so this allows us to kind of look at each term individually. and just continue. We have not evaluated the limit, you still have to write it in. What at this point we can do is look at the summations and see if you can factor the ends out, because they have nothing to do with the summation notation itself. Also constants as well. So if y'all could look at the 8 over n squared had nothing to do with the summation. So I have the summation of I equals 1 to n of I plus, now 2 over n, that gets factored out. Summation, I equals 1 to n. Now when you factor out a 2 over n, there's not a 0, there's a 1 left over. So be careful, maybe I'll write that in red to kind of keep that in mind. So that helps. Now, sometimes people get really confused when there's a 1. So I'll kind of look at this. What I want to do is use formulas for each of these summation notations now. I have the summation of a constant and the summation of an I. Well, let's write this in. Limit as n approaches infinity. I still have this 8 over n squared, nothing I can do quite yet. But I do know the summation of I, that is n times n plus 1 over 2. So that's nice, got rid of the summation there. Still have a plus, still have a 2 over n. And even though, I mean, you might have the formula down from any time you summate a constant, but if you really think about what's happening here, the summation of I equals 1 to n, basically that's like saying 1 plus 1 plus 1 plus 1 forever and ever and ever until you get to n. So what's happening, if this is n times, when you add up all those 1's n times, repeated multiplication gives us 1 times n, or just n. So now I can replace that with just an n. I'm going to see that one more time. And ideally also, if you were, I think that's where this notation comes in. If you have a constant, what are you doing? Constant plus constant plus constant plus constant. How many times? N times. So that's going to give you C times n. So just in case you were wondering, I don't know if we went over that in the preliminary work, but sometimes you can think these through and then you have a better time. You don't have to memorize everything. Just know what summation notation means. Okay, let me double check that. Looks like there's a negative sign there and it's not supposed to be. That is a marking. So at least we got rid of the summation notation, everyone. We're happy. Let's go back. The last thing we have to do is, let's see if we can simplify a bit. That's kind of something to keep in mind. So I have the limit as n approaches infinity. Now, if I were to maybe make this a little prettier, I kind of see some stuff canceling out. The n's, one of them, and 8 and 2 reduced out to 4. So at least I can get 4 n plus 1, 4 times n plus 1 over n. And then the 2 over n times n, well, that's nice. That's just a 2. They reduce out. Now it's a little bit better. Now keep in mind, if you have a limit of a sum, then that is the sum of the individual limits. So we have the limit of 4 times n plus 1 over n, plus the limit of 2. Well, the limit of a constant is just a constant. And this might be where I'm using the Bill Gates idea. Call it BG a little bit. And if you take the leading term analysis or dominant term analysis, the numerator is end up being 4n, denominator is n. If we were going to reduce out, what happens? The n's divide out. And so what do we get is the limit as n approaches infinity of 4 plus 2, we already figured that out, which is equal to, the limit of a constant is 4. 4 plus 2 gives us 6 square units because we are dealing with area. Nice. And maybe we have a better way to verify that later. But take your time. I cannot emphasize enough, if you skip steps, if you miss one little piece, it really throws off the problem, and it's quite frustrating in WebAssign when you're trying to type in the answer. Okay, so I guess it's a little overkill. Maybe you get it by now, so if you feel like you get it, you can definitely, that's the beauty of watching videos. You could shut me off, put me on pause and try your homework and see where you end up, and that's fine. But I'd like to kind of see a couple more examples of using this limit notation. And then we're going to go over one last. So we are almost there. It just takes a while to develop these. So let's play. Example 7. It's the same idea. Again, there's that limit definition. And if that helps you to remind yourself what the limit definition is, maybe you start off by writing what it is. So limit as n approaches infinity, sum of I equals 1 to n of f of x of I times delta x. So then kind of the idea is, you know, oh, I have to eventually get this f of x of I times delta x before I can even do any limit calculations. Hence the need for preliminary steps. First step, calculate your delta x. In our case, endpoint, 3 minus 0 over n. So that's 3 over n. 2. Let's get a formula for x of I. So remember, that's the endpoint, plus I times delta x. So our endpoint is 0. Delta x in our case is 3 over n. So very nice, we get 3i over n for our x of I. Step 3. Calculate f of x of I. Well, go back to our function that we have right here and just use x of I notation. So that's x of I cubed plus 6 times x of I. Now that helps us see what we're looking at. When we're finding who x of I is, now it's just a straight plug-in. 3i over n cubed plus 6 times 3i over n. Now if we cube 3i, we should get 27i cubed over n cubed. 6 times 3i over n is 18i over n. So almost there with the preliminary work. Item number 4 is getting that f of x of I and multiplying it by the delta x. That's finally going to be what we're plugging in. So f of x of I, we just calculated to be 27i cubed over n cubed plus 18i over n. And again, our delta x was 3 over n. And don't forget, with the delta x, it's to your benefit to distribute it before you even start plugging it into the limit. So we should get, okay, so 27 times 3. Save your brain calculator, that's going to give me 81. 81i cubed, but 3 over n, that should give me n to the 4th in the denominator. 18 times 3, calculator, times 3, 54. 54i, and n times n is n squared. So now we finally have our idea of what we're going to plug in. Now we're ready to use limit definition. So when I show the plugin, I have limit as n approaches infinity, the summation of I equals 1 to n. F of x of I, we are going to plug in 81 I cubed over n to the 4th plus 54 I over n squared. Now, we kind of keep in mind, oh, there's a sum. So sum and differences of summations. I have the limit as n approaches infinity. I can now summate everyone. I equals 1 to n of 81 I cubed over n to the 4th plus different summation, I equals 1 to n of 54 I over n squared. Close limit. Now, take your time. Take your time on this for a second. Battery life working on. The next thing you want to do is factor out any sort of constants or n's to help you out with this summation notation. So I see that I can pull out an 81. And let's be clear, I still have everything involved inside. I can pull out an 81 over n to the 4th, but I still have summation notation, I equals 1 to n of I cubed. That's still stuck there. Still have the plus. I can pull out a 54 over n squared, but I still have the summation I equals 1 to n over, well, the summation of I. But now, seeing this clearly, I can replace these summations now with their formulas. So I can get rid of that complication at least. Thanks. That's good. So n approaches infinity. Still have 81 over n to the 4th. The summation of the I cubes, if you remember, n times n plus 1 over 2, but it's squared. Still have plus. The summation, before I write that, I want to write the 54. Let's make sure. 54 over n squared. Summation of all the i's, or just summation of I, n times n plus 1 over 2. That's our multiplication. And we're still haven't taken the limit yet. Now seeing that, it's to your benefit to clean it up before we even try taking the limit. So if we want to play with this, if you want to take a couple more steps, what do I have? I still have 81 over n to the 4th. Sometimes this first part, n times n plus 1 over 2, sometimes that gets you. So what you might be interested in is maybe saying, taking it a little slower. That's n squared, n plus 1 squared, and then what's on the denominator, 2 squared is 4. So if that helps you, I definitely would use it. 54 over n squared. We'll keep that into the idea. It could reduce at this point, but yeah, might as well. 54 over 2, those are nice factors, might as well. So 54 over 2, I should get 27 calculator. I got a lot of things on my mind. Also, what you might be interested in is that one of the n's is going to cancel out with one of the n's here. So that'll save us some time. So I should get 27 times n plus 1 over just an n. And then looks like maybe I should clean up the other limit, or the 81. So 81 over 4, that's still good to go. Nothing's happening there. But the n squares on the numerator will cancel out with 2 of those in the denominator. So that should leave me with a n square in the denominator, but there's also a 4. Okay, so now we're feeling a little bit better here. Now, we have the limit of a sum. I take some liberties here, and I can still write the individual limit, but we can invoke Bill Gates if we understand that we're just taking the limits of a sum is the sum of a limits. So I still have the limit as n approaches infinity, and now I'm just going to take the leading coefficients, or the leading term dominance. So I should have 81 over n squared, no, 81 n squared, excuse me. Still all over 4 n squared. And then also 27n over n. And now we can simplify a bit. Limit as n approaches infinity. Let's look at this, 81 over 4. Nothing to do there. But the n squares divide out. Oh, that's nice. And the n's divide out too. So we have 81 over 4 plus 27. Well, the limit of a constant is the constant itself. So all we have to do is figure out what is 81 over 4 plus 27. And here I'll pull out my TI because my brain can't handle it anymore. But I do know we might want to say, hey, it's square units. Sure, we can combine over common denominator, but let's be precise. So I'm pulling my TI out. You don't have to see this. So 81 over 4 plus 27. If I was going to be precise, I can change it to a fraction. It actually ends up being a nice terminating decimal. But I should have 189 over 4 square units. Voila. You guys feeling confident yet? You will be. One more, and then I think you're going to have this down. So one more computation, and then we'll show you kind of an application of this, just so that we can see. So we revisit f of x equals x squared. And you're like, oh, that'll be nice. And that is true. However, we change the interval on you. Instead of starting at 0, we start from 2 and go to 4. And so that kind of sometimes provides a bit more complication, but we've done enough. We can handle it. So one more time, using that limit definition, what's that area? The limit as n approaches infinity of the summation of I equals 1 to n of f of x of I times delta x. By now, since how we've done so many, you probably have it memorized. It's like second nature. Now, preliminary steps. Step 1, calculate delta x. So that is the right endpoint minus left endpoint all over n. So we're going to have 2 over n. Step 2, calculate x of I. Well, that is left endpoint plus I times delta x. This time our left endpoint is 2. Delta x is 2 over n. Make it a little prettier if you want. 2 plus 2i over n. Step 3. Calculate f of x of I. Well, rewrite your function in terms of x of I. So f of x is x squared. So we have x of I squared. Well, who is x of I? 2 plus 2i over n, but we're squaring it. And so this would be the case, maybe it would be to your benefit to multiply this out. You might have a nice binomial formula you can use, but I'll just rewrite it twice. Saves me some errors. So if I distribute FOIL, I have 2 times 2 is 4. 2 times 2i over n is 4i over n. Another positive 4i over n, and then 2i times 2i and times n. I should have 4i squared over n squared. Clean it up just a little bit more. 4 plus 4i plus 4i, 8i over n plus 4i squared over n squared. So a little more complications. We're almost there. 4. We are looking at calculating the expression for f of x of I times delta x. So we already have f of x of I simplified as much as we can, and square, be careful. Delta x, remind me, was 2 over n. And so that would be kind of beneficial. Let's distribute in. So 4 times 2 over n is 8 over n. 8i times 8i over n plus 2 over n, or times 2 over n, is 16i over n squared. And 4i squared over n squared times 2 over n, we're going to have ourselves an 8i squared over n cubed. So now it's time, everyone. That limit definition, let's replace that f of x of I with our calculations. So let's take that into hand. So limit, as n approaches infinity, you have the summation of I equals 1 to n. F of x of I (8 over n) plus 16i over n squared plus 8i squared over n cubed. We're almost there. At this point, I'm going to take some liberties and kind of tell you that, yeah, you can take shortcuts. So what I have just done, I'm going to take limit notation and summate all at the same time. Let's rewrite it though. Okay, so with my shortcuts, what I'm looking at is I'm simultaneously factoring out n's from my summations. So this is going to leave me with 8 over n. Now that would give me the summation of a constant. So summation of a constant is constant times n, 1 times n is n. Now I can factor out 16 over n squared. I have summation of I. Summation of I is n times n plus 1 over 2. Okay, I can factor out 8 over n cubed. Summation of I squared is n times n plus 1 times 2n plus 1 over 6. So it kind of saves yourself a little bit of writing, if you're able to handle it. If you can't handle it without making a mistake, feel free, write it out, no harm. So now we clean up a little bit. The limit as n approaches infinity, we just simplify 8 over n times n is 8. I should have 16 times n. Oh yeah, I could do this. Okay, so let's say we have what, 16 over 2. We can reduce out a little bit. 16 over 2 is 8. So we have another 8 going on. And now we have the n's. One of these ends cancels out. Oops, I'll write it in red for you. One of these ends cancels out with one of these ends. So I should have n plus 1. N plus 1 over n. And then if we want to do this here, what do we have? 8/6. If you're interested in reducing, what do we have? I have to think because what 2 goes into 6? It's been a while, huh? Okay, so 2 goes into 6 3 times. 2 goes into 8 4 times. See the fractions that end up getting us confused. Ah. Okay, so one of these ends canceled out with one of these ends. So I should end up with n plus 1 times 2n plus 1. Still all over, there's an n square happening. Okay. So now this is where I can invoke Bill Gates for some of these. So Bill Gates. The constant is still there. There is nothing wrong with that. But what I'm looking at is the 8n over n. That's this piece, dominant term analysis. And also I should have 4 times n times 2n gives me 8n squared. Oops, to show you what that looks like. So 8n squared all over 3n squared. So that's me using Bill Gates. Now I'm running into my other work. You want to simplify just a little bit. What do I have? N approaches infinity. I have 8 plus 8 plus 8/3. Now I have the limits of a bunch of constants. I will take my TI. What is that? 16 plus 8/3. I've been thinking too hard already. So use that to your advantage. We should have exact value 56 over 3 square units. And we have utilized that limit definition. So now I'm confident, you guys, we've seen a lot of examples. You've had a chance to write things down. Your hands are probably pretty sore, as mine is. But you now have enough experience to attack these properly in your homework, and you're gonna have a good time with them. It's just a lot of algebra and a lot of bookkeeping to keep in mind. So just one last problem, I promise. This time I really mean it. We're looking at a distance problem one more time. We're going to revisit this. And I want to kind of show you how it relates to what we were looking at with areas under curves. And so we end up having the speedometer readings of a car and time versus velocity. They tell us times in seconds, velocities in feet per second. And if you're looking at this, they've kind of now, instead of X's and Y's, we have things in terms of T's and V's. And if you're looking at this, this perhaps makes a little more sense. I believe that time is your independent variable. And if you look at the distance of the times between each subinterval, it appears that your delta T, they're all 5 apart. They're 5 seconds apart. So that's kind of nice to kind of be able to just look at the chart and really realize what we're dealing with delta T. And what we're looking for part A, they are interested in finding the best underestimate for the total distance D traveled during the 30-second interval. Okay, so what I need to be careful about is that we've been used to using, okay, underestimate appears to be left, but I need to kind of point out it depends on context of the problem. When everything's on a XY coordinate system, yes, the left X value is always smaller than the right X value. But underestimate really means we're using the lower of the two speeds. In the interval. That's not just the one on the left. So not necessarily the left. And you're saying, wait a second, I thought we're talking about velocity, but we're looking at distance. Keep in mind, when we look at what we're ending up trying to find, we're ending up looking at what rate times time equals distance. So just kind of a quick sidebar. Rate times time equals distance, right? Well, rate in our case is velocity. So that's in feet per second. Time is in seconds. So when you find the distance, what happens is the seconds divide out, rate times time, and that's why they're asking for the distance. Because eventually we're actually multiplying these all together. You're like, why? Well, when you make the rectangles, that's kind of length times width based on height. So what I want to pay attention to is let's mark these intervals just so that we see this. See if I can. We're looking at the time interval between 0 and 5. That's the first interval. The time between 5 and 10 seconds, second. 10 and 15 seconds, 15 and 20 seconds, 20 and 25 seconds, and 25 and 30 seconds. So there's 6 sub-intervals. Now, when you're dealing with the underestimates, when you're looking at the first sub-interval, you can kind of say, oh yeah, well, the one on the left with the 30 versus 36, yeah, that's going to be the lowest one. When you look at sub-interval 2, 36 and 40, yeah, 36 is smaller than 40, no problem. Sub-interval 3, 40 versus 48, yeah, 40 is smaller than 48. Sub-interval 4, 48 versus 52, 48 is the smaller value. But the issue happens here and here. When you look at the sub-interval for 5 and 6, the smaller value that we would choose is between 52 and 50, we'd be choosing the right endpoint in this case. And then when you look at sub-interval 6, the smaller value you'd be choosing between 50 and 45 is still 45. So I kind of want to point that out. Those words, it doesn't make sense according to if you're thinking, oh, it's always the left endpoint. You have to deal with the context of the problem to really understand this. So I'll write out generics for you, just in case. I have estimate of distance. Really what we're looking at is always the rate that we're looking at times delta t. So that's the first interval. Second interval, rate times delta t. Third, R3 delta t. Fourth, R4 delta t. Fifth, R5 delta t, and 6 R6 delta t. Now, a lot of you are saying, okay, delta t, we're tired of writing that. Yes, that is true. We can factor that out. So if you want to look at R1 plus R2 plus R3 plus R4 plus R5, my hands are really tired right now, R5 plus R6. Now it's just a matter of who you're going to choose for each of the intervals. We walk through it. The ones that are the issues that are not obvious are the R5s and the R6s. So remember, if you want to do that right away, for R5, we chose 50. And for R6, we chose 45. Those are kind of the ones where they're not the left endpoints. Well, everyone else, it tends to make more sense. We already know delta t is 5. Well, R1, we can then say, okay, that's 30. 36 R2, 40 is R3, 48 is R4. And then the last two were the ones that weren't quite in line with what we were talking about with left and right endpoints. So now, just use your calculator, you end up finding the total distance. I don't believe there's approximation needed, so feel free to use your TI. Those I'll just enter in directly. Yeah, we can probably add them up by hand, but we have gone through about 10 examples already. I'm getting 1,245 feet. That is my estimate of my total distance. And guess what? What do they want us to do now? Let's change it up again and find the best overestimate. Well, same idea. And again, what does this mean with overestimate? You probably guessed it. You're using the higher of the two speeds in the interval. And it's not necessarily just the right-hand side. So distance is still calculated by the length times the width of everything. So we can still go with our formula. If we factor delta t out, that's the base. And the height is going to be the function evaluated. Well, we already are given the function, the values of the velocity. So what do we have? R4, R5, and R6. So we kind of can shorten that out. Now we already know who delta t is, which is 5. Here's where I want to go back. And again, let me erase from our previous problem. We are overestimating. So interval 1, we're going to use 36. No problem there. Interval 2, between 36 and 40, we're using 40. So you're like, okay, it's still the right endpoint. Interval 3, between 40 and 48, we're still using the right endpoint, which is 48. Interval 4, between 48 and 52, we're still using 52. I'll erase that other one, I didn't have that. So 52. R5, let's look at the interval 5. So we either have a choice between 52 or 50, and if we are overestimating here again, this interval is the one where we are now choosing, this time it's the left interval, or the left endpoint, because we want the higher value. R6, also the issue of not just automatically the right-hand endpoint. We are choosing 50, because that is the higher of the two values. And so if we calculate this, you can plug this into your TI. We don't always too many times with our mental calculations. I'm getting this to be 1,390 feet. And if you were interested, a little note, that's all we had to do, overestimate, underestimate. What would be the best estimate? For our total distance is if you take the average. We kind of play with this idea already, but we were kind of thinking like derivatives and slopes of tangent lines. But if you took the 1245 plus the 1390 and you divide it by 2, then the best estimate with seeing the chart that we have, because we have no other ideas of what the function actually looked like, is actually, I'm finishing off with my calculator, I knew it was 1,000 something, but 1,317.5 feet. And so it kind of gives us a better idea, just knowing the information that we know and not knowing what the actual function is. we would be able to take the actual area if we knew what the function is, because you can do the limit definition to find the area. So just so that you're kind of getting this kind of connection of why did I bring this up again with distance and velocity, one other note that might be interested is when we were talking about, you know, using the velocity to talk about the distance. I don't know if you guys remember that if you took the derivative of the position is the velocity. If you want to go backwards, it's kind of what we're looking at is the area under the velocity curve, if we knew what it was, is actually the distance. So it's kind of what we were approaching. We're just looking backwards from what we know about chapter 2, chapter 3. So it's kind of a nice application of a problem in context where, yeah, we don't know what the function is, but we can use the time intervals and then the snapshots given at particular endpoints of the intervals to help us figure out estimates. So I hope you are a lot smarter than you were at the beginning of this section. I think you are. And so I have a feeling you're going to do fine in the homework. Thanks for hanging in there. I will see you in the next section.